Okay, today we'll be doing section 5.2, medians and altitudes of triangles. A median is exactly what it sounds like. It sounds like middle, and it's because it is a segment that will go to the middle of the opposite side. But we also need to know that it has to start from a vertex of a triangle and then go bisect the opposite side. So I'm going to go ahead and draw it right here. Here's a triangle. There are going to be three medians. I'm just going to draw this one from here to here, and it goes to the middle, which tells me that segment is cut in half. It does not tell me the angles are cut in half. It only tells me the opposite segment is cut in half. Okay, if I drew another median, it would say these two segments are cut in half. And if I drew in my third median from the third angle, so that's why we always have three of all these special ones, it tells me these sides would be cut in half. All of them are midpoints now. And now, as you can see, we have a spot where all the medians are going to intersect. And this is going to be important for a couple distances that we are going to want to know about. Go ahead and write this down. The intersection of all three medians of a triangle is located 2/3 the distance away from the vertex and 1/3 the distance away from the midpoint that we just found. This is important, and it looks like it's a fraction, but they're not very difficult fraction. 2/3 is just twice as big as 1/3. So we're saying the distance here from the vertex to the point will be twice as big as the distance from that intersection back to the side. So say this was 4 units, I can now say this was 2 units. So that's very helpful. This is the same thing on this purple one. This distance from the vertex is twice as big. So let's just say this was 3 right here. That would tell me that would have to be 6. And then let's do it one last time. Here's the bigger distance because it's coming from the vertex. And here we have, say this was 5. That would tell me this would be 10. It's just twice as big for that bigger section from vertex to the intersection. Here in examples 1 through 6, I can see that I have medians because I can see that they are all starting from the vertex of the triangle, and then these segments that are congruent indicate that I have midpoints. So I do have 3 medians. I'm going to highlight them all. And then knowing that special distances, I can say one section will be twice as big as the other. So let's see, what do I have first? Over here on that pink median, I see I have 12 units from B to U. So the smaller section would be half that distance, which would be 6. On the purple median, I can see A to U is 16, so half that distance would be 8 for U to D. And then the last one, the green one, doesn't have any measurements. So let's go back to our instructions up here. We already noticed the AU. We already worked with BU. What we didn't see was this CF. And CF is 18. In order to find those differences, we have 2/3 and 1/3, which means we have 3/3, which means I should divide this 18 up by 3. And when I do, that will tell me that the small distance would be 6. And since the bigger distance is twice that amount, that would be 12, which would make up for our 18 total distance. So we can always divide the entire distance by 3 in order to get the smaller amount. All right, now that I have that filled out, let's go back to our problem and see what they want us to find. So first off, they want us to find UD, and we see UD is 8, so go ahead and fill it out. Number 2, EU was the pink one we found. It was 6. CU from top to middle will be 12. And then AD, A to D includes all of that purple measurement. So 16 plus 8 is going to be 24. And then on number 5, U to F is this little distance down here for 6. And then B to E is the entire pink distance from end to end. So 6 plus 12 is 18. So look how easy it was to fill out my answers after I filled out the diagram. So go ahead, fill the diagram out first. You know that the longer section will always be twice as big as the smaller section of the medians. Number 7 is a challenge problem, so we're going to have to read through all the instructions and fill out our diagram as we go. It says AD and CE are medians. Medians mean they go to the middle. So AD, I'm going to cut that one in half. And then for CE, I'm going to cut this segment in half. Remember, it cuts the opposite segment in half. It goes to the middle. And then we also have some information here that AD is perpendicular to CE. So here's CE, and AD is perpendicular. So I'm going to go ahead and put my right angles in here. Just make sure I know those are perpendicular, also forming right triangles if we need them. And then they have AB is 10. Well, all the way across is 10. Tells me if that was a median as I marked, that these each would be 5. That was helpful. And then CE is the last bit of information I can see, and they say that is 9. CE is a median. Remember, I said if the whole thing is 9, we can divide by 3 to get the smaller part. So the smaller section will be 3, and the bigger section will be twice as big, which is 6, and then therefore the whole entire segment is now still 9. So that's all my information in the directions. Now let's go see what they want. They want us to find CA. CA is right here, and it's part of this right triangle. So I do have some information on that right triangle, not quite enough yet, but I have 6 for that lower leg. However, in this triangle next to me, I have 2 segment measurements. It's still a right triangle. I can actually find this leg here, x, by doing the Pythagorean theorem. So that's what I'm going to do right here. I'm going to say x squared plus 3 squared for the other leg equals 5 squared for the hypotenuse. So I have x squared plus 9 equals 25. Subtract the 9, and I get x squared equals 16. That's a perfect square. So x equals 4. So that's helpful for me to know a second leg in that pink right triangle I drew over there. So now I'm going to call this P for a moment, P for powers maybe, and do the Pythagorean theorem one more time. Leg squared, which was 6, plus that 4 we found for the second leg, will equal P for the hypotenuse. I'm going to go with 36 plus 16 equals P squared. And so now I have 52 equals P squared. This is not going to be a perfect square, so I'm going to break it down. The square root of 52 is going to be 2 times 26. 2 and 2 times 13 now. I got a date. It's going to have 2 that goes out. 13 stays in. So my distance for CA equals 2 root 13. So we had to do 2 sets of Pythagorean theorems in order to find our final answer. So that was a bit of a challenge there. Definition for today is an altitude. This is a segment that starts from a vertex of a triangle and is perpendicular to the opposite side. So I have a triangle here, and if I start from this top vertex, I can draw an altitude. From the vertex straight to the opposite side is going to be perpendicular, and all an altitude will do is form a right angle due to the perpendicular segment. It doesn't bisect the angle, it doesn't bisect the opposite side, it just forms a perpendicular, which creates a right angle, which is helpful because now I can have some right triangles going on. Okay, if I already have a right triangle, let's just call this A, B, C, and if I already know this is a right triangle, AC would automatically be an altitude, and so would BC. So sometimes these altitudes are almost hidden. So we have 3 altitudes per triangle. So there's 1, there's 2, and then my third one would start out here, and have to go to another letter, say D. So again, you're going to have 3 vertices, which means we're going to have 3 altitudes. So I can go back now in that first triangle and show you how, oops, they could form one from there and maybe form one on this side. And then one last time, sometimes we'll have an obtuse triangle. And so I just want to point this out. Sometimes in an obtuse triangle, the altitude actually falls outside of the triangle. So sometimes we might have to extend the opposite side in order to find it. So that's what an altitude is. And sometimes they can be hidden, whether they fall outside on an obtuse triangle or maybe they are actually the sides of a right triangle. But we do have 3 altitudes on all triangles. Okay, so my last example of the notes is a proof. So let's go straight to the given. Angle CFD is congruent to angle EFD, and then FD is an altitude. So I like this proof because it makes you use your vocab knowledge in order to complete this. Then this was all given. I'm going to go mark my diagram. CFD would be this angle here. I'm going to mark it congruent to EFD down here. And then that was a set of angles. I think I'm going to try to prove those top and bottom triangles congruent. So that's my plan for now anyway, which is why I marked that as A for a set of angles being congruent. Let's go figure out why they would want me to know that segment FD is an altitude. Well, by definition, an altitude starts from a vertex and is perpendicular to the opposite side. So I have to first say FD is perpendicular to the opposite side, CE. I can't go straight to a right angle. I first have to say I have perpendicular segments. Definition of altitude is my reason. Check it off. And now that I know I have perpendicular segments, I now can say perpendicular segments form right angles. So I'm going to go ahead and say angle CDF and angle EDF are right angles. And that's because definition of perpendicular segments, if 2 segments are perpendicular, they form 4 right angles. So that was a good hint. And now we know that all right angles are congruent. So I can go one step further to say CDF is now congruent to EDF. All right angles are congruent is my reason. And finally, I get to mark another set of A's for our congruent angle set. And then finally, this segment down the middle is reflexive to both triangles. So I am going to say DF is congruent to itself for reflexive. And that's a set of sides. And that's enough information now to say those triangles are congruent. So triangle CDF is congruent to triangle EDF by the method angle, side, angle, because the side was the included side. And now that I have all the triangles congruent, all the remaining corresponding parts are congruent. So I have to figure out what would be the one that helps me out to show that I have a median. Which of those 6 congruent parts? So FD is a median, would have to go to the middle by showing these corresponding parts right there, which show me my segment went to the middle. So I'm going to say CD is congruent to DE. That would be CPCTC. Corresponding parts of congruent triangles are congruent. And now that I showed that the segment F started at the vertex and went to the middle, I can now go ahead and say that FD is a median. And that's going to be definition of median that we learned earlier. And I am all done with this proof, and I am all done with our 5.2 notes, so we will stop right there.